All right. Before we get into the meat of the matter, I just want to give a basic layman's description of what it is, what we mean by PID controllers. No, this is not the technical description that you see in the text. This is basic, like I said, layman description, but I think it helps us to understand what is going on. All right, so suppose we have a satellite dish. And we want to control the angle theta. So this satellite dish is to be controlled by a motor. And we say that we want the dish to be at 60 degrees. So we are going to run the motor. So we are going to have our motor. And so we're going to put in a dial that says pointer or something that says that we want it to be at 0, 60 or 120. So our input, we set 60 degrees. So what that is, we're going to punch in a number, turn a knob, do something, and then we're going to have an electronic circuit of the order of milliamps run that is when we put in the 60 degrees. So, but milliamps cannot run the motor. So therefore, we have to have an amplifier that's going to convert to amps, and then we're going to have a feedback. So it's going to potentiometer, and the potentiometer, so we're about here again. Going to feedback. So potentiometer converts position to voltage current. So we have our system like that. So what we are saying is that when you're going up to your satellite is going up to 60 degrees, towards 60 degrees, the position is going to rotate, and the feedback value is going to be of the order of milliamps. So this is my error signal. The difference between what I want and what I presently have. But the error signal is not enough to drive the motor. So we have to amplify it. And that is what we remember now. The amplifier just takes the voltage or current, input current or voltage, and multiplies it. So proportional control is just taking the error signal and multiplying it to a value that we can get to use whatever our plant is to operate. All right. So when we have proportional control, that's basically what the proportional controller is there for. Bear in mind that I'm talking layman terms. All right. So I'm talking layman's terms. Hmm. All right. So um so that's your proportional controller. All right. So I will make a little note. So so what we are saying is that your proportional controller just serves to amplify the error signal. So this is my error signal coming in, this difference between what I want to amplify it to be able to operate my plant. All right, so that's what the proportional controller. You can look at the proportional controller in that way. Now, so the thing that you're going to be concerned with your proportional controller is what value of K are you going to use? What value of gain are you going to use that will essentially operate the plant properly? You don't want to put the value of K so much that the output becomes uncontrollable. Um, so it's going to go fly past the thing. You don't want to put it so low that it takes forever to reach you don't want to put the gain such that it's going to take forever to go to the value that you want it to go to. You want a response you, you that you determine, right? So your gain that you're going to work out for your proportional controller should operate the plant, but it shouldn't be such that, like I said, it is going to take forever to reach the value that you want. And it shouldn't be such that it is out of control. All right. So that's the proportional controller. So let's talk about the integral controller. And once again, I am saying to you that we're talking um, layman's terms. So the integral controller integrates the error. All right. So let me go back to something here. And I needed to answer some questions so that we can gain some understanding. So let us say that your plant now is a motor. And the output that you want is the speed. So you want the motor to be at 1,000 RPM. So, so you're going to input 1,000. That is what you want in whatever fashion you input it in. And this is my error, the difference between what I want. So now, so my controller now. Questions. First of all, what is the integral of 6 equal to?
60.
What's the integral of 0 equal to?
Some constant.
Okay. So now, let us say that we had a proportional controller. It's just an amplifier going to amplify the error signal. And I want this thing to be 1,000 RPM, 1,000 revs per minute. And I'm at 900. So I'm at 900. I'm at 900. This is 1,000. So the error would be 100 converted to whatever milliamps or millivolts or blah, blah, blah. And so amps and it is current is, sorry, revving up my motor. Cut a long story short. When you are at 1,000 RPM, what is my error going to be equal to?
0.
0. And so if I have, now, the next question is that when you're at 0, when you reach 1,000 RPM, that is the speed that you want to maintain at, right? Because it's 1,000 we put in. Now, if you have a proportional control alone, that means that it's just going to take whatever it and multiply it by a factor and put out that. Whatever value I have inside here, if this is 0, then what is going to be the output on this side if I just have a proportional alone, controller alone?
0.
0. And 0 volts to a motor is going to do what to the motor?
Nothing.
You're going to shut it off. So therefore, but if we have we know that the integral of 0 is a non-zero constant. All right. So when you reach 1,000, when these two are 1,000 and 1,000, then the error is 0. If I have an integral controller inside here, and not just a proportional controller, then my integral controller is going to integrate the error and put out a constant value here. And that constant speed is going to maintain, so that is going to be 0 in and a constant value out, and so forth and so on. So the integral controller, one way of looking at it, like I said, layman's way of looking at it, is that it is going to, when the error is 0, the output of the controller is constant. All right? So when the error is 0, the output of the controller is constant. So it maintains the plant at that value that will cause the error to be 0. I don't know if you understand it because I'm looking at the computer screen, so nobody can judge by looking at people's face. But
Yes, sir.
all right. So All right, so when the error is 0, the output of the integral controller is a constant. All right, so that constant value maintains the plot. So your textbook put it in the other way that if you want 0 error, then you use an integral controller. An integral controller causes the error to be 0. Right? So the other thing that so you need an integral controller. Let me. You need an integral controller when the output is a rate, whether it is speed or you need the constant rise in temperature or constant, whatever it is, when the output is a rate, or rate is something divided by time. So when the output is a rate, then you need an integral controller. So the output is a constant, and then now we're going to multiply it by k, some gain, so that whatever the output is, we're going to multiply the constant value by that k value there. That is a gain as well, but it's a ki times the constant to maintain the plant at whatever value it is. All right, so we need the integral controller when the output is a rate. So, like I said, talking in layman's terms to indicate what it is that before we go to the, just wanted us to understand what the PID is for. So let me go to derivative. All right. So some basic questions now. If I differentiate 60, I get 6. 6,000 T, I get 6,000. And if I 0.060, I get 0.006. All right, so what does a derivative controller do? Well, this is my plant, my my controller. So this is my plant. So my error. So this would be Now, suppose this, you're going to use your imagination. And this is going to be an aircraft. All right. So you know that the aircraft is supposed to maintain a certain height. So it's flying and it's supposed to maintain a certain height. So your aircraft is and it hits an air pocket. So therefore it's going to drop dramatically, very quickly. Now your control system is to maintain it at the height h, whatever the height h is. So you make a big drop. So it is going and it makes a big drop. Now, so look at this thing now. So it was at 10,000 feet. Yeah, I'm American. So 10,000 feet in the air. Yeah. And it starts to drop. Now, and it is this dramatic drop is, let us say that it is 6,000 T. The rate at which it is falling is 6,000 T. Right? So Y is equal to 6,000 T. The rate at which it is falling. Well, let us put the minus in there because it's decreasing. And it's supposed to be at 10,000 feet. So now, what would the error be? The error would be 10,000 minus 6,000 T. This is plus, this is minus. So therefore the minus and this is going to make this positive. I don't know if you see this minus here. We're going to make this minus here. Minus and minus will make it positive. So when I differentiate that, now remember now it's falling. When I differentiate this thing here, what is this going to be equal to?
6,000.
6,000. Okay. So now, in other words, so remember now we're maintaining height. I'm just using it as an analogy. So the 6,000. So in other words, it's going down at a rate of 6,000 T. And whatever the plant is, that is supposed to push it up. Because remember now, this output, the output is height. So if you have a positive output from here, it's going to increase the height. And if you have a negative output from here, it's going to decrease height. So it's going to be a very large positive input to the plant. So it's going to try to push the thing back up to the 10,000. So now, when this is Y equal 10,000, when it goes back up to 10,000, 10,000 minus 10,000, the error would be zero. Different derivative would be zero. So it don't trouble anything if it is at, so this wouldn't fall into effect. If the thing here is 10,000 and the input is 10,000, the difference is zero. The derivative would be zero. So it wouldn't trouble anything. It is going to leave it at 10,000. But if there's a sudden dramatic drop, then there's going to be a countering. The drop is negative. There's going to be a countering dramatic rise in the controller. So now, what about if it is not a dramatic drop, but it is a nice little gentle drop? So let us say that now the drop is negative. Sorry, Let me use a counter example. It's a nice little gentle rise. So it's 0.006 T. So that's what my rise would be equal to. Well, all right. My output would be Y equal 10,000, the 10,000 that I want, minus the 0.006 T. And then my dy by dt will be equal to negative 0.06. So in other words, it's going to gently carry back down. So what I want to make the point is that when there's a rapid change, there's a rapid response to put it back. So if the thing is dropping at a rapid rate, there's a big response to push it back to where it was, to counter it. Now, if there's a small change, then there's a small counter for it. All right. So the derivative controllers counter the noise in the system. Massive change, massive response. All right. So if there's a big change in the derivative, because it's going to the change is going to be the change in the system, because we're taking the derivative of a large change will be a large value. The derivative of a small change will be a small value. So our integral controller, when you want the rate to be constant and the error to be 0, derivative controller, when you want to take out the noise, and if so a system that is prone to noise, whole heap of noise, then you want to get rid of the noise is really a spike. So you want to get rid of all of those and just maintain it at one constant value. So the derivative controller is there to counter that. So so just to make the point now.
Yes, sir. One is error reduction and one is noise reduction.
Right. Very good summary. One is error reduction and one is noise reduction. All right. So that is what we want to bring across to you. That is why you hear about the PID controllers. All right. Why they are the most commonly used controller in industry. Because like I said, I just love that summary there. One is error reduction and one is noise reduction. All right. So that is why we have those. And the PID controller, unlike our pole placement and all those other things, is not based on the response that we want. In the sense that we are, with the pole placement, we're fixing the plant to behave in the way that we want. How long it will take to rise, how long it will take to do X, Y, and Z. What is our settling time, what is our overshoot, and all those type of things. So we're fixing the pole so that we can do all of those. The PID controller is basically just to make sure that the plant goes to the value that we want it to stay there and it is not prone to any error. All right. So that is why we have those. And the PID controller is basically just to make sure that the plant goes to the value that we want it to stay there and it is not prone to any error. All right. So it is resistant to any noise in the system. Right? So, so bearing that in mind now, um, I know the board is there spinning and looking at me. All right, so we'll find a way around that. All right, so I want to talk today about our PID controller. And everything that we are going to talk about with respect to the PID controller is not done analytically, it's done empirically. So empirically, it means that we have over time an experiment that is what um, over experimentation over time, we have come up with these values. So with whatever we're going to say. So it's not analytical, it's empirically done, experimentally done. All right.
Excuse
So
me, sir.
mm,
So is there like a case where the noise or the noise like will cause a system to malfunction before um the the derivative controller could fix it, sir?
well, um,
Because
yeah.
it seems there's a delay between how long before the before the controller would realize. So that's what I'm asking. So, yeah.
Oh, the delay in the system is dependent on the system. Is um and the layers of the system. I was going to bring up the point of the plane that crashed. Um, when Boeing withdrew all their aircraft, um, the aircraft was let's see if we remember how what was the problem. But it was a control system that could be overridden by mankind. So see all of those self-driving cars and things, it was a self-flying plane, basically. And it needed and it needed to be at one point to be overridden. So what happened now was that if the plane, when the plane was descending, I sat down and read about it. When the plane was descending, the, the, the error signal was saying that the plane is descending at a we're gonna above. If the plane was descending at above a certain rate, then the controller was supposed to pick up, and the error was supposed to say, all right, cut down on this. But there was a point at which the person was supposed to take over because the plane was supposed you're supposed to I can't remember how they go again. The plane, the basic thing was that it was the plane thought it was landing. So and it didn't allow the humans to take over to say no, it's not like the plane landing. So it stayed in a little loop. So it read the incoming error as supposed to be normal. I refused to correct it, even though the person tried to get back control to say this. No, we're not landing. We're really going down. So it continued to push the plane down because it said this is a normal landing routine. So the whole system is it crashed the plane itself because the programming was supposed to say um, when when we started to descend at a particular rate, it's not land we landing. It don't care what it is. Maybe we hit a air pocket descended but what happened was that the plane continued descending and they couldn't override it because it wasn't built for human override of the system. So it basically ended up crashing the plane because of that. So in other words, the noise because of the air pocket or the rapid descent for whatever reason end up crashing the plane. So Boeing had to withdraw the aircraft and one whole lawsuit. And I don't know how come they're still in business, but they're still in business. All right. So let me just deal with the chapter. Chapter 10 in the Ogata is on PID controllers. Now, there are several methods of control that are there, but the one that we are going to be focusing on is the most popular one that exists, and that is Mr. Nichols and Mr. Ziegler's rules. And like I said, they are empirically determined. Empirically means by experiment. Analytical means, so let me spend a little time explaining the difference between empirically and analytically. How do you solve this? X squared plus 4x minus plus 3 equals 0.
Yeah, factorize it. That's very good.
All right, so you can factorize it. And what else you can do?
Think you can complete this square. So go.
All right, so we can complete the square. And we can use the formula as well.
Yeah, use the quadratic formula.
All right, all of those things are analytical. If I say, well, put in 2 inside and see if it works. And you put in 2, and you say 2 squared and 4, all right. No, try minus 2. And you say minus 2, and then I say try minus 3. And you try minus 3, and so forth, and you try numbers until it works. And then you might say, well, try the negative of the number that is over the constant term. Put that in first and see what you get, and then work from there. That is empirically. You try until you get a response. So what I'm saying is that this is empirically determined, i.e. trial and error. All right. So that's the first thing that we wanted to point out, that it's trial and error Mr. Ziegler and Mr. Nichols use. And there are other methods. Tuning just determine the gains KP, KI, and KD, the gains of the system. So whenever they talk about tuning, that is what they're talking about. Whatever methods that they use for determining the gain. All right. So as you see here, numerous tuning rules for PID controllers have been proposed since Ziegler-Nichols. So, but it's only Mr. Nichols' method them talking about. Now, the other thing that we need to point out is that what is said here, but there's a diagram that says it better. Mr. Ziegler and Mr. Nichols' method are, when we tune in a PID controller and what we're going to discuss, it will give you 25 to 40% overshoot And like we said, it's going to give you error 0, and it's going to be resistant against it's going to be resistant against noise. All right. So it's not a matter that we are going to say that. Remember now, in the other case, we determined what was the overshoot that we wanted. We determined what was the length of time it's going to take to settle. So with our TS and our TP and all those type of things. No, this method doesn't deal with that. It says that you're going to end up with 25 to 40% overshoot. You don't business with settling time, you don't business with rise time, you don't business with peak time, you don't business with any of those parameters. And so it's not a matter that all it is a method that reduce the noise resistant, error resistant. All right. So Mr. Ziegler, Mr. Nichols' method is basically that when we apply the method, that is what we're going to end up with. Sorry there, go back. Okay. So the first thing that we want to talk about is the tuning rules for a first order system. Right? So tuning rules for a first order system. And you have, so let us say that the system gain is K. The lag time is L. This T is time constant of the system. And somebody can tell me what time constant, what's the definition of time constant?
Time taken to reach 68%, 63. Whatever.
68 is fine, or 66 is fine, or 67 is fine. 68 is fine. Right? So the time constant is the time it takes to reach 60% of the final value. All right, so the lag time, let me draw an ugly graph. All right, so we're saying system gain is K. Lag time is T, and time constant. Lag time is L, and time constant is T. A better graph. The lag time is the time it takes the output to respond. So this is my input. At time t equals 0, it goes to a value. So this is my input. There's a delay or a lag. time before the system responds, and that time is L. All right. Now, we need to be able to determine these values. So you can determine them experimentally. So how do you determine them experimentally? You put a unit step onto the system. Whether the unit step is 1 volt, 1 degree Celsius, whatever the unit step is. And you graph the output response. Now the graph of the output response, you have to determine certain things. So the final value is K. When the system levels out, the final value equal K, as is here. You have two ways in which you can determine the time constant. Because by the definition of 63% or 68% or 67%, depending on the 60 odd depends on what it is. And you can measure the time from which it starts to reach 63% of the value. And you know that that is your time constant. And your lag time is going to be the time it takes before it moves to the output moves to a non-zero value. Now, this here says differently. What it says is that you find the line of steepest slope in your graph, and then you draw the line of steepest, draw a tangent to the line of steepest slope. If you draw the tangent to the line of steepest slope, then where it cuts the axis, and between 0 and where it cuts the axis, that is your lag time, and between where it cuts the final value and initial value, that time is your time constant. So this is your input, sorry, your output response, and you can find out all of these. Now, as usual, of course, we do business with that as much. But look at this a little bit. Tangent line at steepest slope, and where it cuts the axis. That is where that is your that is your sorry, lost my train of thought there a while ago. So I was saying, look at this a
Lag
little
time.
bit because that is your lag time. All right. So I want to do something a little bit that is not in the text. So we're going to shift from this and go back to the whiteboard. Oh joy. You don't know why I'm saying oh joy.
Whiteboard, come up, sir.
Yeah. Yeah. What my intention was to put the thing beside the whiteboard. But all right. So let me draw a little graph and then let me ask some questions. Okay, so let us, the typical response, this is a typical first order response. So let us say that our output is our voltage, and the typical first order response for voltage or all those type of things is V naught 1 minus e to the minus t over CR. Now, what will be the final value? When you hear the noise in the background?
Yes, sir.
So, excuse me 1 second. Let me just. All right. So what is the final value in this situation here?
So VO.
All right, so this is my final value. So final value is equal to 10. That is my K. What is my that is going to be my time constant?
One over 0.2. So
Time constant in this one here, so it would be, my time constant would be the CR.
mhm.
So therefore would be
0.2 inverse.
so that is going to be 5. And that is going to be my T. So now the next thing that I need to find out is my L. All right. So how do I find my lag time L? Now remember, it is the time it takes for the line of greatest slope to cross the y axis. All right. So where is my line of greatest slope going to occur in the graph that is here? Going from here. So this is 10. This is 0. Where is my, what point is my line of greatest slope going to occur?
Right after L.
All right. So in between here and here, what between 0, right? When I say between here and here, I not realize that I'm not pointing at it. Between 0 and 10, where would my line of greatest slope? What value on the y-axis would it occur between 0 and
5.
5? So I can find, and so can I find the value on this axis where the line of greatest slope occurs?
Well, that 5 would be what the gradient. We can use that.
All right. So here's what I'm going to do now. I'm going to put in, so V equal 10 minus e to the minus 0.2 t. And I am going to say that, first of all, that at greatest slope,
That not supposed to be 10e. When I expand the bracket with the 1 and a 10.
sorry, 1 minus,
Yeah.
so 5. So at greatest slope, 5 is equal to 10, 1 minus e to the minus 0.2 t.
Just transpose for t.
So I'm going to transpose with t. So we have 5, sorry, 5 is equal to 10 minus 10 e to the minus 0.2 t. So that's going to be minus 5 is equal to minus 10 e to the minus 0.2 t.
That is 0.5. ln 0.5 is equal to negative 0.2 t. Negative 0.2 t. ln 0.5 over negative 0.2.
Somebody can record that. Calculate.
3.47.
All right. So so 3.47. So this is going to be 3.47. Anyway, 3.47. And over here, so it's 5. All right.
Hold on, sir. So we use is the time constant, the 60 something percent we use. I forgot the minute I asked. Continue, sir.
No. If it's the 63%, we use to find the time constant.
No. Well, we have the 5. We arrive at 5 on the y-axis.
But just saying it's halfway. Just
so
whenever use the 63, whenever use the not the time constant value we did use.
okay, because yeah, all right.
I mean, sorry, it's not this 5 here that we used to put the 5 here. But now that we're thinking about it, if it's 0 to 10, the time constant is 63% of the final value. Yeah, we work out that.
So it would
But
be
that would
6
have been
point
time
something.
it take to reach the maximum value.
Yeah,
So it
63,
would work.
right. Oh, all right. So now, the little lag time is taking a bit of a, going to take a little bit of work. So this is a line. And so now we want to find this, a line, the equation of a line. Yeah, no, let me not do that. We're going to say equation of a line. What is the equation of a line? What do you know the equation of a line to be?
Mx plus c.
All right. So y is equal to mx plus c. I prefer use y minus y1 is equal to mx minus x1. That's one of the things that I'm teaching in a math class. So we know a point on the line. It's 3.47 is the x. So y minus 5 is equal to mx minus 3.47. So we need to find m. But m is a gradient. So all we have to do is differentiate this to find the gradient. So dv by dt, what's that going to be equal to? Well, we have to differentiate what is inside the bracket. So it's going to be 10 times, what about this now when we differentiate this?
Minus 0.2 e to the minus 0.2 t.
That's minus 2e to the minus 0.2 times, and the value of t that we want to find, that is 3.47. So that is going to be equal to. So work out that for me, someone.
Minus 1.
Minus 1?
Yes, sir.
Something all right.
So what that when you differentiate, what that value give again?
The gradient.
Or you don't need if you find L, the log time.
Yeah, the log time. Because we're going to find the equation of a line. And then something is amiss. Reason why I say something is amiss because this line is a positive slope and we're getting a negative slope. Differentiate 1 minus. Oh, yeah. This is supposed to be plus. So what when you change the sign, it is going to be equal to what? 1?
Say 1, right? Yeah.
All right. So now, so the equation of the line is y minus 5 is equal to 1. So we're just going to be x minus 3.47. So now we want to find the log time. So it should have been a t. Let me put a t here. It's not x. X-axis is time axis, so it's a t, not an x. This thing is giving me all kind of problems. The response. Taking it one time to do whatever it is that you need to do. I understand. All right. So this is supposed to be a t. So when y equals 0, we're going minus 5 is equal to t minus 3.47. Or t is equal to minus 5 plus 3.47. Again, problems again. Let me see what is the issue. 1. X minus 3.47. Then 0.2. 0.2 times 3.47. You sure is 1?
Let me check it again.
In the car. Check it again. No.
It's minus 0.2 times 3.4. Yes, sir, it's 1. Or 0.9991.
So the difference when I differentiate, when I try to follow the part and look away, because the 10 would have still supposed to be in front of that.
Yeah.
So the 0.2 would have been 10.
That'll be 10 E. Right.
Oh yeah,
Yeah, but
it
it expand it.
Right. Right.
So when you put in the 0.2 times 3.47 and then exponential that times 2, you get everything be a 1.
0.999.
Because it's giving me a negative time. I'm wondering why it's supposed to give me a negative time.
Oh. Yeah, let me look back on it.
Give me a second, I will check something.
So I wonder if the x1 value would have been the 3.47 and the x2 value would have been t.
No, these are m y minus y1 and the y value of 5. And this m x minus x1. So this x1 at 3.47 and this would have been the t. And the m at the gradient which is get as 1.
So sir, why not 10, sir?
Why is not 10?
Yeah, from a
Because
graph.
multiply this by 2. So we get 2. Alright, we're now going to help on it. Some mistake make somewhere, and probably maybe before the end of the class we find it. We just like when no. Alright, 10 e to the minus 2. Carry this down. 10 to positive 2 e to the minus 2t. T is that. So the gradient is that. 2 times a half, the gradient is 1. Y minus that. Oh, yeah. Oh, no. Yeah. You see me the foolishness. No, like.
Sir, what happened to that minus 10 we're on the left hand side, sir, before we go over to 5 equal minus 0.2t?
Where the 10?
But we have minus 5 equal minus 10 e to the minus 0.2t.
And then we this is supposed to be, no, the thing they mess up. This is supposed to be 0.5. No, this is supposed to be 0.5, yeah. So,
You're right, man. You're right, sir.
yeah. So ln 0.5 equals, so this is supposed to have a ln in front of it.
Yeah, yeah.
So let me just check that there. So ln 0.5 divided by 0.2. All right, so that's a 3.47. So that is correct. And this is 5. So that is correct. Feel like I make a mistake. Anyway, I'm not gonna do it on it because that is the point is not the maths. So let us say that t is equal to whatever we get, and we're working with it. Negative 1.5 seconds. So this would be my log time is equal to, I'm going to use negative 1.5 seconds in this case. All right. So the whole point about going over here, we find what the, because some fundamental error makes, so I'll find it and tell you what it is in a little bit. But that we digress it, because the main point of the exercise is that if we have a first order response, so let me go back to this now. You see in the chapter 10 in the book, I don't know what you see.
Just seeing your photo, sir.
You just see my photo. Oh, okay. Do that again. All right. You're seeing it in the book here.
Yes, sir.
So these are the things that we need to find: L, T, and K. The final value L and T. But I was just making the point that we can, if we have the shape of the curve in the form of an equation, then we can find out what is L and T and K analytically. All right. So whether we have it graphically, we can just draw the tangent line and determine L and T and K. However you determine those things, then here are the tuning rules. And again, just making the point that the tuning rules are determined empirically. So then how I'm get them there? So once you determine T and L and K, okay there. Oh, it's a K here. Once you determine those values, then you now have to choose the controller that you are going to use. Now, so a lot of times we get lost in the mathematics, and it's not the mathematics that we're supposed to get lost in to determine, because we are here as the teachers, we're talking about the L and the T and the K and the this and the that and the that and all those type of things. That is the least of the problem. The engineering person has to know whether I'm going to choose a proportional controller, a proportional integral controller, or a proportional integral derivative controller. Which one do I choose? Well, here is the rule. Here is the thing. If you have a system, and most of the, sorry, let me digress again. Most of them come And if you look at most of the equipment that is going to use a controller, it comes with a P and I add D, and you fill in the values and your work. Now, and so the other thing that I'm pointing out is that if you notice here, there's no transfer function that you need to know. Right? If the transfer function is known, or not known, is not an issue. If the transfer function is known, then we can work out an analytical value, and we can work out T and L and D analytically. If the transfer function is not known, then all we do is plot the graph, like I said before, draw the tangent line, find the K, find the L, and find the T. So the thing about it now is that you have to determine what kind of system that is that you have. So the common sense discussion that we had before, if it's prone to noise and you want to control the noise, then you need a derivative controller. Notice that you only have three choices. It's either proportional alone, proportional and integral, and proportional, integral, and derivative. It's your choice. It's not a matter that you must fill in the values. You must have a value for D, and it's your choice whether you're going to just use you just need proportional control, proportional integral control, proportional integral and derivative control. Now, if you notice the example that I started with, when you just had position, all you need was a proportional controller. When you had a rate to control, then what you need was a PI controller. And then when you had to add noise, then you have a PID controller. So, for example, systems like thermal systems, like the big old furnace that they have out of Jamaica, it take every 15 minutes you take a measurement to determine what is going on inside the system. So the graph with the Y and the time, this here can be 1 hour. There's no noise spike on that. So therefore, this is out. You don't need a PID controller for systems that change slowly and there's there is not prone to be affected by any noise. Where the noise may come from when you have a furnace operating at 1100 degrees Celsius. What is going to add to that temperature here? All right. So the noise is not a factor in those things. So you have to determine whether you want whether anything is susceptible to noise or not, to determine which one of these you are going to use. So after you have done that, then now you can work out KP, the gain for the proportional controller, the gain for the integral controller. This is not KI, this is TI. Now, let me just make a point here. If you look at inside here, let me just write it down that KI is going to be equal to KP divided by TI that you determine here. And KD is going to be equal to KP times TD. All right. So the gain for the system, KP, we can work out KP. That is, we can work out TI, but after we work out the TI value, depending on which type of controller you're choosing, then you work out TI, then you can work out the gain Ki. And then if it is a PID controller, then KD. That is going to be 0.5 L. So let me bring up our first order response and
L
then
there being the log time, right?
lag time. L is the lag time and T is the time
Time
constant.
constant. Okay.
So I'm all right. So we're going to bring up our first order response and then we'll work our way through it. So give me a second here. All right. So we have a system and we can determine K, P, Ki, and Kd. Sorry. Yeah, pen. Sure. All right. So this is the response. Yep. Okay. So if you look at the graph, for example, in this graph here, this section here, the lag time, we could easily read it off. L would be equal to 2. And then now, from 0, remember we said it was 63%? So this is 2. And this is the time it takes to reach 63%, which is from 2 to 5. So therefore, that would be 3 seconds there. All right. So L
So yeah,
equal
Peter,
to,
that's why I did wrong the first time because we did have 5 and I never must 5 to find it when I'm using the tangent to the curve.
right. Well, that is true. But in for example, in this particular case, the line of steepest slope would be here, so
Yeah, because that was given. So the other youth when they say probably we should have find 63% of the 10 and wherever, well, it would have
And
been 6.3.
6.3, right? So
Probably that.
make we go back and use the 6.3. All right, so this now, T now would be 3, and K would be equal to 10, although we don't need K in this particular scenario. So we have L, so you can look at the curve, work out 63%, and then work out the base, just look at the graph and work out the time. Based on that now, so L equal 2, T equal 3, K equal 10. So in our situation there now we had L equal to T equal 3, K which we don't need equal 10. So now let us say that we had a furnace. My favorite example, my go-to example. Which one of these three would we use?
Or the P or the
Furnace,
PI.
P or the PI. And we always go with PI. We never normally go with P. Fine. Anything at all, no matter what. Even if it's P would have worked. So PI. So now our KP is equal to 0.9 times T, which is 3, over L, which is 2. That's 1.5 times 9, which is 1.45. If my head still work, and it's not necessarily working. All right, so what would be my TI?
Yes, sir.
So here you go about the formula. When I remember we had it right.
1.35, sir.
How much?
2 divided by 0.3.
2 divided by 0.3. So much 0.3. So 2 divided by 0.3 is so much. My head now function. 10 over 3. 6.67.
Yes, sir. And the next one at 1.35, sir.
And TD is equal to 0.5 L. 0.5 times L, which is 2. Oh, wait, how much you get? Oh, wrong thing, man. L divided by 0.3. We don't need TD. So I'm doing this. This is foolishness. Rubber.
0.5 times 2. Yeah.
But is this one we use? It is the
Oh, yeah, I just realized. I go for the PID one.
mm.
Yeah.
All right. So now we need KI. So KI now is going to be equal to KP divided by TI. So that is 1.45 divided by 6.67. Somebody tell me what that work out. Somebody tell me, say we need a battery. We need a new phone, but we need a battery for the phone.
0.22.
0.22. So KP is equal to 1.45 and KI is equal to 0.22. So that is how we would sort that out for that.
So what is Ki again?
The gain for all right. When you have an integral controller, you excuse me 1 second. All right.
Yeah,
So,
where do you find K? Okay, we follow, we follow.
all right. So, um, we forget what we was saying before. We said KP and
AI.
KI. What was KI? All right. I don't think we did make it clear before. So maybe we just go back to the drawing board a little bit because it was in my residual thing to say. I needed to talk about KI. What is KI actually? So we could just have a little brief discussion about. All right. So remember what we were saying now. Whoops. Draw straight. Remember what we're saying now. So the integral, we'll go back. So you have your integral controller, which is the integral of the error. All right, and the error is the input. You have your plant, you have your output. And so now we say that the integral, if the error is 0, then the output is a constant. Because if you integrate 0, you're supposed to get a constant. So your motor going to see a constant voltage, and so your output is whatever it is. The Ki is how much you multiply that constant by, right? The tuning for the controller is the, so you take the error and multiply it by a constant. Because you still, remember now, the constant value that you're going to get is going to be of the order of milliamps or millivolts. Still going to be small. It's a constant value, but it's small and small non-zero constant value. So you still have to multiply it by a gain to get it to control whatever it is that you want to control. All right. So,
So repeat that again, please.
all right. So remember, let me use the example. So this was 1,000 RPM, and this was 1,000. So when you feedback, you read this is 1,000, this is 1,000. And your error is 0. I would say that the integral of 0 is equal to a constant.
Yeah.
All right, so it's a non-zero constant. So what we're saying now, remember now, if I said RPM, and this is 1,000 RPM, the system not going to is going to take the RPM that we have and convert it to some, let us say, some electronic conversion is going to go and it's going to convert it to something of the order of some millivolts. Remember, the sensor that we're going to be using is going to operate and it's going to change the voltage or change whatever, detecting what the speed. So it's going to be of the order of millivolts or milliamps or some milli something. So now, when the error is detected and we integrate the error, it's going to be the constant that we're going to get, still going to be of the order of millivolts and milliamps. So if we have to run our motor don't run off of millivolts or milliamps. It runs off of volts or amps, so we still have to multiply it by a constant to bring it up to the value that we want. It's going to be a constant value because the two constants multiply by each other. But so the Ki is the constant that we multiply by. So when we tune in the controller, we're going to say, when the error is 0, we're integrating and we multiply by a constant. And that constant is Ki. I don't know if it may make any more sense.
So it's just a gain, sir.
It's just a gain. All the three, the Kp, Ki, and Kd, all of them are gains. So this one is the K. Remember now, the whole entire system is Kp times the error plus Ki times the integral of the error plus Kd times the differential of the error.
Differential of the error.
So that's the output. So we multiply the error by a value. Each of these, these are the gains of the system. And when we find these, we say we tune in the system. All right. The method that we use to find KP, KI, and KD now, remember now, we can use pole placement. Or we can use, now we are talking about, we can just use the tuning for the PID controller. So here is the reason why the tuning method that we talk about for the PID controller is the most popular. Because up to this point, you don't hear me mention the word transfer function. For the
That's
pole
what
placement,
you didn't say. If the transfer function is given, then so be it. We use it. But if not, we can use this method.
you can use the method and work your way through it. So, and I challenge anybody, I don't know if anybody work anywhere, I challenge you to go anywhere in Jamaica and say to them, the system that you have, what is the transfer function? I challenge you to come back and get an answer. Miki, how much? Well, $1,000 to anybody will get an answer. Full money, but if and there's no system in currently that I know of in Jamaica, most of the parts of the world where they know the transfer function. Because most engineers can't bother to work out no transfer function. And so them just resort to PID control and just use that. So it is, pole placement is nice and it gives you better things and all those type of things, but you have to know the transfer function system for it to use pole placement anyhow. So this is a method this is the go-to method for all industries. Because this don't matter if the transfer function, known, unknown, it don't matter. But so you have to work out the gains, and the gains of the system that you use to control the error. Remember now, so like I said, this one is nice. This one is error. Zero error. And this one, just make sure so the plant to operate properly. And you notice that all of them have to have a KP. And then you decide whether you want a PI controller. And by the way, they have P, PI, PID, PD. All right. This one here is just when you want to control noise. But back to the original question, the gain of the system, the gains that we work out, we have to multiply by the gain. So, all right, let me go back to the other one to make a point now. So remember we were talking about the plane, and this is 10,000 feet. And then the plane starts to drop at 6,000 feet per second. And so the output, the error would have been, this would be 10,000 and this would have been 6,000 times T. And it's a drop. So the error would have worked out to 10,000 minus 6,000 T. And we say when we differentiate it, we get 6,000. Now, so let us say 6,000. 6,000 volts, 6,000 volts, obviously, we're going to have a problem. Even let us say that the whatever the system was, the electronic system was 6,000. Could I use 6,000 volts? Question is, the one where your mother did ask you when you pay for the exam. Where may I get it from? Where may I get the 6,000 from? All right. So you're going to have to multiply that by a factor that can work with the motor. So that's what the gains in front do. So if when this is 6,000, so therefore this would have to be like 0.3 or 0.03 times the 6,000 to get a workable or usable value that you can use. You understand? So these are the modifiers are the the ones that calm down. That tell whatever the error is to calm down. Sorry, I was just somewhere with Bridget and think about KD as the girlfriend. So film head around hot. And she is there to tell him. Say, so the lady in the class, flip it please. They did go in at KFC for buy a film when the foolishness start. The KD is there to modify, to say, calm down. This if you just use the error alone and the derivative of the error alone, the response is going to be too much. So the KD is the modifier. Same thing with the KI and the same thing with the KP. You know if I'm making any sense.
Yes, sir.
All right. So I'm going to, since we're not in any rush, I'm going to do the second order system next week. All right, so we're going to talk about the second order system next week. And how it is that we deal with that second order system when we have it. All right, so I'm going to stop there for today.
Sorry, now try back to 6.3 before we leave.
All right, make we go try about the 6.3.
Yeah.
Mm. Mm.
Like a computer freeze, man.
Again, that's how it always that from evening.
But
So
sir,
yeah,
regarding assessment, so you were saying something that there's a test coming up and all of them something there. And you
no,
being skeptical.
yeah. So what I'm going to be doing is that I'm going to give you the assessment to go home and work out, and then we give you this the test as a multiple choice. We're going to convert it to multiple choice and give it.
Okay, when we can expect this, sir?
Well, um, like I said, basically we have 2 matter lectures left. So any 2 or 3 weeks after that, I'll give you because every year the one assignment is a take-home assignment, and you get 2 weeks to carry it back. But that assignment that you get to take home is usually very similar to the final because same question because all of the material would have been covered.
Okay, so when you say we have 2 matter lectures, that means we have 2 class, like class, 2
Yeah.
lecture class. That not so bad, sir.
And when back in the day, they used to tell you, say, yeah, when you're studying, they say, yeah, poor matter. So that's why we tell you, say, yeah, poor matter lecture. To
Uh,
well,
but
this is foolish, it's just a spin. You know.
try one next one, sir, see if it open. See if that a problem.
Right. But the problem from evening, I just realized it work off of Microsoft Edge. So when Microsoft Edge give problems, it give problems see the Microsoft Edge stop work. I know why Mr. Gates now come sort out in system them instead of run up and down and try vaccinate the whole of it. And you hear the latest thing that him want to know. Synthetic meat. All right. So make we go again. So y equal 10 to 1 minus e to the minus 0.2 t. And so we say that final value is 10. And we want to find out now. So t k equal 10. And then now from 0 to 63% would be 6.3. And 6.3, what that would be equal to? So 6.3 equal 10 minus 10 e to the minus 0.2 t. So that will be minus 3.7 equal minus 10 e to the negative 0.2 t. So 3.7 divided by 10, that is going to be e to the minus 0.2 t equals 0.37. So we're ending up with negative 0.2 t equal ln 0.37 t equal ln 0.37 divided by negative 0.2. So much that work out to be for t.
4.97.
4.97, almost 5. And so we say now y minus y1 equal m t minus t1. If we use the t now. So that's y minus 6.3 equal m t minus 4.97. So we need to find m. So we have to differentiate. This whiteboard here, you have to use a new page. So beg pardon, you have to write all over the place.
Yeah, right, you walk up right up. That's right.
So dy by dt now are going to equal to 2 e to the minus 0.2 t. So is equal to 2 e to the minus 0.2 times, well, we say t is 4.97. So what dy by dt equal to?
0.47.
4.47?
0.47.
0.
0.74. 0.74.
0.74. So therefore is y minus 6.3 equals 0.7. Well, what am I saying?
Hold on, sir. Go back over there. Oh, you get 0.74 there again. Oh, you just plug in everything.
Yeah.
Okay.
Yeah, so that is going to be 0.74
0.74 times t minus 4.97.
So now
Y, oh, yes, yes, Y has 0.
this y is 0. So negative 6.3 equal 0.74 t minus 0.74 times 4.97. So here what everything here.
So 3.678, 3.68.
So now when you
So we
carry,
get a negative number for x, I get minus 3.54.
you get so that make it even worse. Mm.
If you get wait, let me see. Something there don't have a negative in order for you get a positive value. But
Mm.
you know logical. The gradient, the value you get for your gradient will have to be negative.
Yeah, because we have to get a positive gradient. So the gradient have to be positive. So we don't know how come what it is.
Maybe say you choose the 10 and the 0.2 out of the book it come from. You choose the 10 and the minus
No, I
4.
was saying that if this is the response.
Oh. I said maybe it invalid and not work together. That's all.
Listen, this is 6.3, and then we find the time. So this is our time constant. This is our time constant. This is our tau. This is our k, the final value. So the log time, this gradient at that point. When we get the gradient at that point to be that value, something wrong. Here.
So we differentiate 10 e to the minus 0.2 t. The minus 2 you're supposed to get.
Yeah. No, but this minus here go with this minus here.
Okay.
To become positive. Let me tell you what is it, because we can't figure out the issue yet. The gradient have to be positive. So that gradient here have to be positive. T has to be positive, and the T is 0.9. And this Y here has to be 6.3. 0.74, 6.3.
So remind me why is 0 again?
Why is it? Because you want the line.
You
You
know,
want
some
the line to cut the axis, the tangent line, although.
Okay, so okay, all right, sir.
Yeah, the line will cut the axis. So you want the point here.
if you said the T, we have T1.
Wait. Let me say this here, so this right here, so is the log time. That's what I want between here, so and here, so.
That means that T1 would have been 0. You shouldn't need to find the T1 where we put in as 4.97. Or then that the log time is 4.97 then.
Yeah, you can use it as 4.97.
That would have that may look on that would have must be the log time, because the x value them would have be one of them would have be 0 to wherever the time go, and that if that time would have be the 4.97. Just as how you use the y value, the first y as 0, and then the next y would have be 6.3.
Mm-hmm.
That's how I look on it. I look on the log time as 4.97. You
Yes,
find
sir.
it long time then.
Time, sir.
Oh, but wait a little bit. We say y equals 0. This is the gradient. Gradient of 2. And we want to find where this line crosses the y-axis. This value of t will cross the y-axis. Yeah. We want the y x-intercept. This value here. So.
So that means the only T what I find would be the 4.97. It can't be nothing else. Unless we are go
There is something fundamentally wrong, you know. Y, the equation in line is y minus y1. And this is y1 equal mx minus x1. We want the value where it crossed it, where y equals 0. So I'm going to see why it should be working out. The gradient is positive and this thing over here. So why it work out to be a negative value?
I don't see it there, but if that are the case, then whatever value we get, even though we subtract it from 4.97 then. Because it's like I want a little triangle form right now, maybe right there. So.
Right. We're going to look at it and then tell you next week exactly what is the mistake we make, because some mistake. Oh, no.
And there wouldn't be two x value then, sir. Because he only cut the x-axis at one place.
Yeah, but I think if the fundamental problem is with this, you know. I'm going to look at it and tell you exactly what is I think the problem is with how I write out. Because what is it? V is equal to V naught 1 minus e to the minus t over CR.
Yeah, something like that, yes, sir.
So V equal V naught 1 minus e to the minus 0.02 t. So CR, the tau would have been 1 over this.
So that look right to me.
Yeah, we look at it and tell you next week what is something has gone awry somewhere. We look at it and we tell you what. But we don't see, because what that I tell me said this supposed to have a look like that. And it doesn't. I think this curve here is supposed to have a different equation. But we're not sure what is the unless you're going to come next week, I'll tell you, sir. Mr. Monday, I'll tell you relations.
So this in our book, right? Where you get the example from?
No. It is in no book. Hush. The only thing the book them tell you is the same thing like what is here, what is on the screen here. It only tell you how to do it graphically. So graphically, this tangent line, point of inflection, you have to find the point of inflection, and then the lag time is where it crosses the axis. That's all I'm telling you. Them but I said, but
Sir, guess what, sir? Guess what I'm saying? I see it, sir. I see it.
yeah.
You see, based on this tangent line, the x values them would have be. You see, where the tangent line cut the x-axis. You see the t they were refined.
Mm.
Hold on. I'm not chatting no foolishness. We just glimpsing and the brain start freeze up and out, sir.
It's going to go on worse than that as time passes.
Theo, 2t not Theo.
Yeah,
the first t I time constant that I value after a log time from the log time to t.
And that would have been the 0.2.
That would be the 4.9.
But no man, remember so the time constant a big T, you know. So what we find that means that what we just find is time constant and not log time.
We find the time constant to 4.9 that they happen after the log time.
Yeah, but
yeah.
what I was doing was finding the gradient. But then,
So why we not just use the entire time and then subtract the time constant from if we find a log time?
well, you can do that. You can, yeah, do the work
Yeah,
out,
that,
the entire time and then subtract. All right.
subtract.
Well, but I still need to find out why is it that it not work, because it's supposed to find the equation of this line and find out where it cross the axis. Suppose you can do that. And this point, them tell you says a point of inflection. So, um, hmm? So, all right. Next week we come and I will have a proper explanation as to what is the problem. We are not seeing anything right now. Now we probably need a proper first order response. Analytical first order response, and then because if this is your typical first order response. Oh,
So what is 1 over e to the minus t? That not supposed to can give you the time right where you try to pinpoint right this.
oh no, we just realized what happened. Just realized what happened. Just realized what happened. This is for a log, but the equation we will have for the output. No, we don't want our foolishness. Next week.
Yeah, next
Because
week. Okay.
through me have time now, we can sit down and tell you next week. This is plus. And the output is going to be, it can be plus because it wouldn't level up. So I have to go sit down and think about it a little bit. Because it should give a negative log time. All right. So next week we talk.
All right, sir.
All right.
Next week.
Yeah.